In 1911, in Leiden University in the Netherlands, a Dutch physicist was testing the properties of metals at extremely cold temperatures. Known as Mr. Freezer to his contemporaries, Heike Kamerlingh Onnes had succeeded just 3 years prior in being the first physicist to liquefy helium, something which required extremely cold cryogenic temperatures at pretty much just above absolute zero, the coldest possible temperature in the universe. At the time, there were 3 competing theories as to what would happen to the resistance in metals as the temperature tends down to absolute zero. The first theory was that as the temperature tends to absolute zero, the electrons in the metal would freeze, they would stop moving, therefore predicting that the resistance would tend to infinity, because electrons are what carry the current. If the current can't flow, then resistance would be infinite. The second theory was the complete opposite. It stated that resistance was caused by electrons bouncing off hot ions vibrating around in the lattice. As the ions stop moving at absolute zero, this theory predicted that electrons should completely stop scattering, therefore saying that for all metals, resistance should be tending to zero at absolute zero. The third theory broadly agreed with the second theory, but added one more thing on top. It said that yes, there was this thermal contribution to resistance, but there was another contribution, which came from inherent defects in the metal, which temperature has no effect on. Therefore, this theory stated that yes, whilst the thermal part does decay to zero at absolute zero, the part coming from defects doesn't change at all, and therefore the resistance should tend to a finite and fixed value, which is dependent on the purity of the metal. Now, Kamerlingh Onnes' initial measurements seem to confirm this third theory. He used platinum, and as he cooled his platinum down to very low temperatures using liquid helium, he saw that the resistance was tending to a small but finite value. And as he used purer platinum, he saw that this finite value was decreasing down towards zero. He theorized that if he could try this method with a very pure metal, he should be able to get a resistance which is very close to zero. Fortuitously, he actually had such a pure metal at hand. His lab, through distillation, were able to create samples of extremely high purity mercury. So taking a sample of mercury, he repeated his experiment. Once down to liquid helium temperatures, he measured the resistance of mercury and put in his notebook with some satisfaction that the resistance was practically zero. Now, at the time, he didn't realize that he'd made a startling scientific discovery. That's because, remember, he was expecting a resistance of near zero based on his theory that pure metals should have an extremely low resistance. And the fact he was measuring exactly zero, he just chalked up to the fact that his measurement instruments, which were not really designed for super low resistance measurements, just simply couldn't resolve the very small numbers that he was measuring. So for this reason, 3 months later, he repeated the experiment, this time using a much better, higher resolution way to measure resistance. He was expecting to see a small but finite value of resistance for mercury at 3 Kelvin, but what he saw instead absolutely shocked him. He saw that the resistance, even with his new high resolution method, was still reading exactly zero. That meant that the resistance of mercury at this temperature was at least 10 million times lower than it was at 0 degrees centigrade, a mind-bogglingly small number. Even more confusingly, the resistance was measured as zero for any temperature below 4.12 Kelvin, and above 4.12 Kelvin, rather than increasing gradually up to a higher number, it discontinuously jumped to a finite resistance. Subsequent experiments with alloys of mercury were also shocking. Contrary to Onnes' initial theory that impurities in metals were detrimental to their electronic properties, what he found was that alloys were also completely able to exhibit this zero resistance phenomenon at low temperatures, but they actually were able to transition to it at a higher temperature than the pure metal, making them in some ways better than the pure metal rather than worse. Further experiments showed that lead and tin exhibited this same zero resistance phenomenon, which was in some ways a relief because working with mercury was a bit of a nightmare. At this point, this phenomenon had a name. It was called superconductivity, with the materials that exhibited it called superconductors. At this point, Onnes was understandably very excited. If it turned out that superconductivity was indeed a genuine physical phenomenon, then clearly its applications could be game-changing. One application that Onnes had in mind in particular was that if superconducting coils of wire could truly be used to hold very large persistent currents, then they could be used to generate a persistent, almost permanent magnet-like, extremely strong magnetic field which required very little energy to maintain. To test this theory, and to try to discover exactly how low the resistance of superconducting wires was, Kamerlingh Onnes devised an ingenious experiment. He took 2 identical coils of wire, one made of lead, the other made of copper. He placed a permanent magnet in the middle of the lead wire and cooled the coil down to 1.8 Kelvin with liquid helium, causing it to pass through the superconducting transition. Across from the supercooled lead coil, he placed the copper coil, and exactly in the middle between the two, he placed a compass. Whilst both wires had no current, or had the same current, the compass needle would point exactly north. If one wire had a current greater than the other, the imbalance in magnetic fields generated would draw the compass needle towards the coil with the greater current. By removing the permanent magnet in the center of the lead coil, he induced a current in the superconductor. He then increased the current in the copper wire until the compass needle pointed back to due north. By measuring the current in the copper, he could then infer the current in the superconductor. The idea was that over time, if the superconductor truly had some small resistance, the current would gradually decay, causing the compass needle to drift towards the copper, which still had the stronger magnetic field. If he could then gradually decrease the current in the copper wire such that the compass needle always remained pointing north, he could continually measure the current in the superconductor as it decayed over time. Over more than an hour, the needle did not move. Remarkably, the current in the superconductor remained perfectly constant. The ultimate proof that superconductivity was indeed a real phenomenon. Onnes immediately began trying to create incredibly strong magnetic fields. He had a dream of trying to create fields of 100,000 Gauss, or around 10 Tesla. But unfortunately, with his lead superconducting coils, he was only able to get up to fields of around 600 Gauss before they ceased to superconduct. Now, 600 Gauss is around the strength of one of those small ferrite ceramic fridge magnets, so not particularly strong, unfortunately. Now, whilst this was disappointing for Onnes, it was still quite a major discovery. What he found is that it's not just temperature that can knock a superconducting state back to a normal state, you can also do it with a really high applied field or a really high applied current. Now, indeed, these things are actually related. If you have a superconductor in its superconducting state that's much, much lower than its transition temperature, the current and field you have to apply to get it back into its normal state are much higher than if that superconductor was really near to its transition temperature. Kamerlingh Onnes' work did not go unrecognized. In 1913, he was awarded the Nobel Prize in Physics for his work on the liquefaction of helium, which also recognized his broader contributions to the field of cryogenic physics, including superconductivity. He died 13 years later in 1926, aged 72. It was not for another 31 years, about 46 years after the initial discovery, that a microscopic theory of superconductivity was finally established. The theory, called BCS theory after its creators Bardeen, Cooper and Schrieffer, was immensely successful and led to another Nobel Prize in 1972. In the end, whilst he was a little early, Kamerlingh Onnes' dream of incredibly strong superconductor-based persistent magnets has in the modern era become a reality. Rather than using pure metals like he envisioned, like mercury, tin and lead, we instead use alloys like niobium tin or niobium titanium, which we typically split up into very small channels and put inside copper wires. These are used in applications like MRI machines, particle accelerators like at CERN, and in nuclear fusion test reactors to generate very, very strong magnetic fields. What's absolutely amazing about these is that the superconductor is so conductive that the copper, which wraps it, actually effectively conducts none of the current at all, meaning it really acts like an insulator, much like rubber acts around a normal copper wire. In fact, the copper is really only there for its thermal properties. It's because it conducts heat to and from the liquid helium that the wire is immersed in to make sure the superconductor remains cool. Whilst superconductivity research has come a long way in the last 114 years, it's clear that we still have a ways to go before we can really realize the true potential of superconductors. The main thing that research these days focuses on is the creation and stabilization of a high temperature superconductor. And by that, I really just mean a superconductor that could be cooled by liquid nitrogen rather than liquid helium, because liquid nitrogen is significantly cheaper and easier to produce. The main engineering challenge lies in the fact that at those relatively high liquid nitrogen temperatures, it's very hard to sustain a resistance-free superconducting state in the superconductors that they're making. Now, if you're interested in that and you want to learn a bit more about the engineering challenges of making these high temperature superconductors, please leave a comment down below and I'll make a video about it because I think it's a really interesting area of material science. So with that, thank you very much for watching. See you later.